Hello, hello, hello. Welcome, hello world. Alright, so we're here and we're gonna go ahead and take a look at the next problem. So I'm trying to be somewhat disciplined, I guess, about like working on these problems. You know, daylight's what do they call that? Daylight is a waste in here, so we gotta work. Gotta work. Alright. So I have a plan. There's the next step. So, right, trying to get more familiar with Clojure, solving some of the easy problems. The last easy problem we did, I was struggling a bit, so I figured we should do another easy problem rather than, I was going to go to medium problems, but still trying to get familiar with the syntax and all of that. Best way to do it is to actually write some code with it. So, yeah, so that's what we're doing. And we'll just keep going, I think. What else do we want to do here? What else is there? Yeah, just keep going. I think we'll just keep going. That's what we're gonna do right now. Wish to buy video games from the famous online video game store Myst. Usually all games are sold at the same price, $P. However, they are planning to have the seasonal Halloween sale next month in which you can buy games at a cheaper price. Specifically, the first game you buy during the sale will be sold at $P, but every subsequent game you buy will be sold at exactly $D, less than the cost of the previous one you bought. This will continue until the cost becomes less than or equal to $M, after which every game you buy will cost $M each. For example, if P is 20, D is 3, and M is 6, then the following are the costs of the first 11 games you buy in order. Okay, so all games are sold at price P. A sale. First game you buy during the sale will be P. Every subsequent will be D less. Continue until it becomes less than the M, after which everything will cost M. Ah, okay, this is a neat problem. So this is like a linear, what do they call that? Linear sequence? What's the name of that? When you've got, it's actually two sequences combined, right? It's going to be, after a certain point, it's a constant sequence, and then the other, and up to that point, say, I guess a constant difference sequence, something like that. I'm not sure what the name of it is exactly, but it's an interesting thing. So what's interesting is we can do this. I'm probably going to ask, all right, you know, if, yeah, do you have enough money, or, oh, how many games can you buy? Oh, that's a little more interesting. I was going to say, so if you wanted to get the sum, well, you could still do this. It still works. Basically, you can write a function to compute, actually in constant time, how much it's going to cost you, given a certain number of games, how much the games are going to cost. So the way you would do that is the sequence. Basically, what you would do is you want to get this sum, or you want to figure out how many terms down you've got to go until you've hit M. So what that would look like is probably, you could do a little bit of math to do that. So let's do that. This is a good problem. It's an interesting problem. So it's sort of one of those sort of easy enough problems that you know you could solve it, but okay, all right. Got scared there that I might lose the stream. Sort of an easy enough problem where it's definitely doable, but there's enough sort of math in there to make it satisfying. But yes, I definitely rank this as right, easy problem. So, okay, so you got P, D, and M. Given P, D, and M. So we're gonna make use of a simple not geometric sequence, simple sum. This is sort of a well-known fact about summations, which I use quite a bit, or have used quite a bit in the past. Continue to use for problems like this to sort of make the sort of optimize the code, I guess, make it perform these sums a lot faster. So so anyway, what you're gonna do is you got this P, D, and M. P is the initial price, D is the difference, M is the stopping point, and then you've got some S dollars, right? Now, once you've reached M, so what you want to do is there's a sequence, right? P minus D, P minus 2D, P minus 3D, etc. Right? You want to know when, you want to know, you can call this 1D, 2D, right? P minus KD is less than or equal to M, where K is an element of the positive integers, not including 0. All right, this is sort of what we the equation we end up with, and then we want to say, okay, let's say, so what does that mean? So solve for K is really what we want. We want to know what K is supposed to be then. So K is going to be M. You could do it this way actually. You can do it this way. It's better, I think. Oops. P minus M less than or equal to KD, and then so then K is greater than or equal to P minus M over D, right? Okay, and then now what you can do is you can take the roof of, so one of the properties of the roof of a value is that it's always greater than or equal to, it's the next integer that's greater than or equal to, it's defined to be, this is by definition. So, yeah, oh, just one moment. Yeah, good morning. Hello. Yeah, yeah, thank you. Okay. So, what I'm going to do is, then that means that what we want is K is the first integer that's larger than this. It's greater than or equal to this. So that's going to be, sorry, a little distracted. Yeah, that's going to be the point at which the sequence changes, right? Exactly that point. So you can determine that in quickly. Now, this sum, right? And it actually starts with P is 0 here. So the sum of P minus D, P minus 2D, etc. We can sort of rewrite that as like I equals 0 to some arbitrary, I guess we'll call it K, and that's going to be P minus I times D, right? We could consider this case, maybe not use the same K, maybe use something else. Let's use like J, or I don't know, some M, not N, yeah, N, I don't know, M, something arbitrary. It's not. Now, the reason we want to do this is that we can rewrite this now as M times P, or rather, it's actually, so this interesting part is there's an extra P in here, so it's M plus 1 times P minus this sum, minus D times the sum I equals 0 of I to M, which then brings us to M plus 1 times P minus D times, now we can apply this formula up here, right? The one we had, let me show you that one again. That's why I pointed out earlier. I could show you the proof for that. It's kind of an interesting proof, but the basic idea is that if you've got a sequence of numbers all the way up to n, you can group them as sort of n plus 1, n minus 1. Actually, let's do it more clearly. Right, like this. You can say n plus 1, n minus 1 plus 2, n minus 2 plus 3, right? Each of these are going to be terms, they're n plus 1, and there's going to be, because you're using 2 of the terms, the sequence is going to be, there's going to be n over 2 of these pairs, and they're going to be of value n plus 1, right? And n plus 1 is n plus, so you have n plus 1 plus n plus 1 plus n plus 1 dot 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 n over 2 times. Yeah, that's sort of the quick and dirty explanation for why that's the case. You can also prove this inductively as well. It can be shown. So anyway, we can put m here, replace this, right? So now we have a constant time algorithm given some m to compute exactly how much it's going to cost us up to this point of m. Now, the thing is, if p minus kd is less than or equal to m, that means that we're going to be looking at, it's not going to be p minus kd for that particular case. So actually we actually want, for this sequence, we want roof of k minus 1, really. Sequence changes at roof of k. Yeah, roof of k minus 1. Okay. And one more step would change it to m. So there's one more piece here, which is, I think you can use the, no, you want the roof. No, you want the roof. The roof is part, yeah, the roof is fine. The roof, I was gonna say you can use the floor, but that's not really gonna go to work. So you actually want the roof of k minus 1. Okay. So that's fine. So this is the equation given, so basically what this becomes is total cost of PDM given PDM and some k, we'll call it, is going to be this guy. Oops. Oh no. Yeah, it's fine. M is, what is M? Oh no. Oh, I'm sorry. I should have used M here. That's my mistake. I used M up there. I should use J, I guess. Or some, we'll just call it alpha. Some alpha value. I apologize. Given some alpha, we say this is going to be alpha plus 1 times p minus d times alpha plus 1 over 2 when alpha is less than or equal to roof of k, or less than roof of k, which is this expression, p minus m over d. And then this total cost is going to change to TC of, now there's this breaking point, right? P minus m minus d over d. It's going to be the roof of, right? We can just recursively, somewhat, not really recursively, but just referencing backwards, this plus, and this is going to be the difference of, it's going to be I guess, m times alpha minus this roof of pm minus d, p minus m over d. Like there's kind of a lot of, not a lot of math, but there's a little bit of math here. Just kind of makes it neat, kind of makes it satisfying. Morning, brother. Productive way to start the day. How's it going, UKK? Welcome back. Hello, hello. Welcome, welcome. Yes, sir. Trying to do something. I mean, I gotta like, I know I got work I gotta do, but I gotta just like do things. In particular, I have a plan. I have a sort of overarching goal theme of things to do, but I don't do them, one step at a time. I won't get where I'm trying to go. But yeah, yes, sir. I want to be productive, absolutely. And thank you for watching. Also, I appreciate that. Watch me do some maths in the morning. It's kind of you to do. And a few minutes, I'm gonna try to do this quickly, this problem, and then I've got an interview. It's kind of awkward, but basically I'm going to interview for a job that's really close to my home because I want to be closer to home, and then see how that goes. It's sort of something part-time on the weekends, I think. And then once I've got that going, then I'm going to start looking for the next moves. Applied for any new companies? Kind of, not really. I haven't applied to any like programming companies. There's a few I've looked at that I thought would be pretty good, but I'm still kind of I don't really fit the bill completely, the ones that I've looked at. I'm still kind of uncomfortable thinking about it. I probably could get in anyway, but I'm still kind of mulling it over. But yeah, there's a startup I've been looking at that's like, I think would be a good fit. We'll see though. I don't know. Not sure, not certain. And then I was even thinking I could, on HackerRank here, they've got a whole bunch of jobs now on their like apply to jobs type thing, which I guess the idea is that you would go through their sort of interview process through HackerRank, which could be good. It could help me a lot. I think sort of streamline the process. There's a few companies I've been looking at though. I haven't applied to them yet, but I'm thinking I do need to practice a little bit more for some of them, because one of them I was looking at uses a lot of OCaml. You could probably guess what company that is. So OCaml is so niche, but the deal is, if you learn OCaml, that company is rather successful, and because OCaml is so niche, it's like I don't want to say it's guaranteed that you'll get the job, but like there's not a lot of supply of people who know OCaml. There's not a lot of, so therefore you're sort of like really competitive if you can reasonably demonstrate that you know OCaml well enough to help them out. So that company I was looking at, it's like, that's not bad. So yeah, there's a bunch of companies I've been looking at. But yeah, thank you for asking. Appreciate that. Haven't applied yet. I did some OCaml when I was in Goldman Sachs. It's not Goldman Sachs, although it's interesting that they use OCaml. If you know that they use OCaml, I didn't know that. I'd have to look. It's probably online. I mean, they probably do use it somewhere for a company like that. They're pretty big, but no. I don't want to like belabor the point. But basically, if you type in OCaml finance, it'll be like probably the first company that comes up. Yeah, so there's a lot of opportunity. There's a lot of stuff, a lot of opportunity. Really optimistic. Unfortunately, though, do need to like practice more. That's okay. That's okay. This is what it is. But yeah, man. It's good to see you. Thanks for popping in and saying hello. I appreciate that. I'm gonna return to the. Hopefully this doesn't come off rude, but I'm gonna return to the problem. And yeah. Okay. So, but yeah, no, I definitely, you're right. I do need to apply. It's like can't get a job if you don't apply. It doesn't work like that. So what's it doing? Okay, yeah. So we use this total cost of this value just before we make the switch over to getting M, right? So this is sort of, we're modeling this this description, this sequence, which is going to start from P, decrease by a difference D, at each step, each time you buy the next thing, and then it doesn't go below a certain m, and after every purchase after that is going to be m amount. So you can model this in this way. This p minus m over d, this roof of it, this will be exactly the point at which you have to start using m, and so this is going to be after that point of p minus m over d. Now I kind of wish I let k be p minus m over d, so that way the roof of p minus m over d, that way this could be sort of a little cleaner. But yeah, this is what it's going to look like, and I think this is exactly right. Yeah, the m times that, whatever this difference is, all these extra pieces at the end. So using this formula, now this is constant time, right? This is a closed form solution, or closed form calculation. Now if we have s, we want to know how many, how big can we make alpha? We want to maximize alpha. So we want to say with s, so fix, so this is kind of cool. This is called currying, by the way. We fix p, d, and m. I learned that. I was learning about functional programming. Currying is basically, this has 4 variables, but you can consider it as a single variable if you just fix these 3 values. Suppose that they're constants. Basically assume they're constants. And consider TC of alpha. Oops. Probably a C is kind of awkward to use when you're using parentheses. I should just use T. So TC alpha, we want to say TC of alpha is whatever this total cost is. It's got to be less than or equal to S. But we want to find alpha such that it's the maximum possible alpha, meaning TC of alpha plus 1 is greater than S, and then TC of alpha is less than or equal to S, right? So we want to find alpha that satisfies this equation. How do we do that? We want to say, Now the first thing we can check is if we're over this boundary or not. If alpha is going to be, we could say, is alpha, let's say let k be this breakpoint, which we said is the roof of p minus m over d. Let's see. If we let k be the roof of p minus m over d, then I want to say, is alpha greater than k or alpha? Oh yeah, there's actually missing something here. This could be, either of these could be less than or equal to p minus m over d. Right, if it's equal, then this goes to 0, and you just return. Yeah, so it's the same thing. If you put equal on either side, which is kind of neat. That's kind of nice. So it is a sort of as a function, it's sort of, I don't say it's clean. I don't know how to describe that. Like it's continuous, I guess. Sort of continuous function. It'll be interesting to think about this equation in real numbers, real values, rather than integers. You know, that's kind of interesting. I mean, yeah, it's sort of kind of needs to be integers, but interesting. Anyway, well, not really. The p minus d doesn't need to be an integer. The m, no, it doesn't need to be integers. It could be. The only thing that really does need to be an integer is this one. But yeah, they could be doubles. So anyway, so are we greater than k or less than or equal to k? Right, this alpha, that matters a lot. Actually, it matters. We can split this into 3 cases. Alpha equals k, or alpha is greater than k. See, the thing is, if alpha is equal to k, that means that this is this equation, and then this one is the next equation down here. If alpha is greater than k, then in both cases it's this equation. And then finally, if it's less than k, how much less than k though? We know it's not equal to k, but it could be, it really could be, really should have different cases. I think it should be alpha is less than k minus 1, or these are really the cases that are interesting. There's sort of how we cross this boundary. Alpha is less than k minus 1, then we're not crossing any boundaries. We're considering this one in both cases, both sides of this s. If alpha is equal to k minus 1, then we have this k minus 1 here, k here, right? That would am I doing this right? What am I doing here? I think there's 4 cases, right? It's both sides can be on this equation. The left side could be this equation, the right side could be this equation, or both sides could be this equation. Yeah, that's really it, right? And when does that happen? That's exactly, forgive me for kind of stumbling here. Let me think about this. Less than or equal to k. So it could be k minus 1. Less than or equal to k minus 1 is going to put you at, if you're equal to k, or we just do it this way. That's fine. We can just do one by one and see if we're equal to k, k minus 1 equal to k, and then greater than k, right? These are 4 different cases. So if we're less than k minus 1, then it's both on the same side, right? If we're equal to k minus 1, then this is going to be right. K minus 1 is less than this. It falls in this category, and then equal to k, right? K minus 1 plus 1 is k, so this is less than or equal to k, so it's the same side. So this could be combined. And then if we're equal to k, then it actually doesn't matter, right? I think if we're equal to k, both of these end up being the same thing. So it's fine. Or no. One of these will be k, and the other one will be k plus 1, which k plus 1 puts you over. Yeah, that's the part I'm kind of getting stuck on, confused about. So, yeah. Okay, I'm sorry. There's 2 cases. Alpha is less than or equal to k minus 1, or greater than or equal to k. Yeah, of course. Which is just greater than k minus 1. Oh my goodness, I don't know why my brain, like, it couldn't fathom that for some reason. It's an easy problem and really simple, the logic, but it's not wasn't registering. Yeah, less than or equal to k, you're gonna get this, I think. No, but isn't there a spot here that, oh, it can't be right. Yeah, well, because it's continuous, right? So if you're equal to k, you're gonna get technically this equation, the k plus 1, no, it's k minus 1, yeah, k plus 1, k and k plus 1, anything greater than that, greater than or equal to that. So if it's, I'm so confused. If alpha is k, yeah, that's what this is. That's fine. Anything greater than or equal to k here is going to give you k here, and then k plus 1 there. Fine. Oh, no, these are different. No, these are very different. What am I doing? Hello? Uh-oh. No, I think I have good reason to be confused. If alpha is k, then you get this equation, and then k plus 1, you get this one. If alpha is k is greater than k, it's a different case entirely, because greater than k means you're looking here, and k plus 1 you also, okay, yeah, so there are 3 cases. Yeah, I knew that initially, but it just, for whatever reason, my brain is not processing that properly. So there are 3 cases. Okay. And now if we consider each case one by one, k minus 1 and k. So this one we have sort of both sides of are on the same function. This case, one side is on the lesser function, the other one is sort of on the other across the boundary of this piecemeal function, and then this is, we're on both sides of the same piecemeal function. And the reason I want to make this distinction, by the way, you might be wondering why am I putting so much time into all that, is because I think it greatly simplifies this question. This actually can't really be answered reasonably unless you know where k is, I think, or where alpha is with respect to k. Or I think well, I'm actually not sure. I'm not sure how they're related. I think they might be related. That's what I'm thinking. I don't know how I have to think about it some more. So what can be done is we want to know this alpha such that S is greater than or equal to TC alpha but less than TC alpha plus 1. And this actually what answers the question that they're looking for. Now how can we do this mathematically? Now obviously we can use a loop to do this, by the way. This question, you can do it in linear time, but I think we can do this in constant time, which is what we're after. We can do some maths here. So what do we do? Well, I guess you could consider each case and just verify each case one by one, all 3 cases. So what you would say is consider this case. Well, for starters, I think what you can do is take the difference between, in order to know if you're in which case you're in here, right? You could take S minus TC of alpha is greater than or equal to 0, right? We need this case, and then we say if alpha is greater than k, right, then S minus TC of alpha has got to be greater than or equal to m. Right, that's not necessarily the case. That means that so you can actually check. Yeah, I think you can use this sort of use a sort of predicate to determine this. So basically what we're suggesting is if we subtract this sum up here up to the sort of maximal point, if we subtract that sum from S and there's still enough left over to subtract another m, that means that we must be in the case of alpha greater than k, right? Where alpha, because alpha's got to be, TC of alpha's got to be less than or equal to S. We can use these formula to imply that. If alpha is equal to k, then s minus tc of alpha is greater than or equal to 0, but s minus tc of alpha is less than m. Right? Necessarily, right? Because that means that we're if this implies that we're greater than or equal to m, I think I need to get going. I'm gonna have to come back to this. You know what I'll do? All right, a couple things. Yeah, I need to get going. I wasn't expecting this to take so much time. All right, few notes. One is we can come back to this point and continue. I am going to end the stream here. What I'll do is I'll take down the stream. I'll restream after I go through the interview. Restream, take down this stream. After that stream is done, then I'll actually cut a video and combine the two streams into one consolidated stream. So that way, like, you can see the whole process here, figuring this out. By the way, this is something I probably should be able to do this a lot faster, but for whatever reason, I'm like really going slow here, really slow going through the maths. But yeah, this seems to be the way to do it. You can use some logic to say, okay, if alpha is greater than k, you have this implication, and we know that if alpha is greater than or equal to t minus k, is greater than or equal to 0, right? This actually implies both of these things. If I want to say if alpha is greater than or equal to k, then s minus t alpha is greater. No, but this is always true. This is always the case. Excuse me. No. This is implied from, we get this from here. So we know that this is by definition of s. Actually, that's by definition. So we don't need to justify that one. So we have that by definition. Then we say if this, then that, which implies that not this implies not that, which is less than or equal to. This would imply alpha is less than or equal to k. Right? And then if alpha is equal to k, then it's not, right? It's not this, so you gotta have alpha less than k, or less than or equal to k. Now we just need to consider the alpha less than k case is left. So you could basically perform a few checks and then probably deduce what s has got to be. Sorry, not what s has got to be, what alpha's got to be, given these equations and these deductions. So pretty neat. We'll come back to this. So yeah, thank you for watching. I've got to go take care of something important, and I'll be back probably in like an hour or so. And I will talk to you all soon. And yeah, I'll cut the video that I make. I'll live stream again this problem, and then cut the video, put it into make one video out of it. I think that's a good idea, because this kind of problem, like, this is kind of neat. I like this. This is I think not a bad thing to have. Like maybe I can cut it, make it like a 10-minute video, speed it up, something like that. So I'll be back.